I would like to recall that if f is a differentiable function, then the average change of the function on the interval between x sub 1 and x sub 2 is just the difference of the f's over the difference of the x's, which means we have f of x sub 2 minus f of x sub 1 over x sub 2 minus x sub 1. This is the rise over run, as you remember. This is the slope of the line between the points x sub 1, y sub 1, and x sub 2, y sub 2. Okay, it's this. It's the secant line, as we called it before. This is the run, and this is the rise. We also were talking about the instantaneous change of a function, that this is just the derivative of the function at that value of the x. So the instantaneous change of the function at x equals a is just really the limit of this secant line. It's the limit of the difference of the f's over the difference of the x's, which is just f prime at a. This is also the slope of the tangent line at x equals a. So here's the tangent line. Let's talk about blood that flows through an artery or a vein. We assume that the blood vessel is a cylindrical tube with radius r and length L. The blood flows faster along the central axis, where the friction with the sides of the tube is the smallest. So here's the center axis. And when the distance from the side is decreasing, the friction is increasing and the blood flow is slowing. So let's see the following law that put everything together here. So the speed in centimeter per second of blood in an artery of radius capital R and length L, that is r centimeter from the central axis, is modeled by S of R equals K times capital R to the power of 2 minus R to the power of 2. Pay attention, the capital R is a constant, okay? It's the radius of the artery, and the small r is, as it's written here, is the distance from the central axis. And what is this K? Well, this is just a constant that is described by P over 4 nu L, and P is the pressure difference between the ends of the artery, and U is the blood viscosity. So this is just a constant after all. That depends, as you can see, on L, which is also the length of the artery. An example. Approximate the speed of blood flowing in an artery of radius 0.007 cm and length 12 cm at distance of 0.001 cm from the center. Let's assume the numbers for P to be 3,500 and for nu to be 0.021. First, we have to evaluate K. We just substitute those numbers, okay? L is the length, everything is in centimeters, so that's why L is going to be substituted as 12. Okay, and then obviously the P and the nu you just copy. We are using a calculator, and we get that. Now when we have the K, we can substitute everything in the function S of R. This is capital R, is the radius of the artery, and this is the distance from the center. We substitute those numbers using calculator, and we get that. The exponential growth model is the following. We assume that some quantity grows or decays proportionally to its amount, and here's the initial amount to be q sub 0, and k, the growth or the decay constant. Then the quantity times t, q of t, is given by the initial amount times e to the power of k times t. Example: assume that some population obeys the exponential growth model with k equals 0.23. Given that the initial population was 2,000 individuals, let's find two things. A, the average growth of the population between the end of the first year and the end of the fourth year. B, the instantaneous growth of the population at the end of the first year and at the end of the fourth year. We are going to use the exponential growth model with initial amount of 2000 and k is 0.23. So the number of individuals at time t in years is given by 2000 times e to the power of 0.23 times t. The average rate of change is just the difference between the amounts in the end of the fourth year and the amounts in the end of the first year over 3. So at Q4 we just substitute 4 for t, and for Q1 we substitute 1 for t. Using calculator, we get approximation of 833 individuals per year. So this is the average rate of change. For the second problem, we need to take the derivative because we are talking about instantaneous rate of change, and because we are going to use it twice, once for the end of the first year and then for the end of the fourth year. I'm just going first to take the derivative, and I'm getting 460 times e to the power of 0.23t, and in the end of the first year I'm going to substitute 1 for the t, and we are going to have change of 579 individuals. And for the fourth year I'm going to substitute 4 for the t, and I'm getting about 1,154 individuals. It is clear that we are going to get the rate of growth to be proportional to the existing population size. This is true to any exponential growth or decay model. Example: assume that after t hours, the concentration of some drug in the bloodstream is given by C of t equals 0.02 plus 1.9 over cubic root of t, where C is in grams per liter of blood. Find how fast is the concentration of the drug is changing 3 hours after an injection. Is it increasing or decreasing? Because we are asking how fast, this is rate of change, and because this is at exact time 3 hours after an injection, we have to take the derivative of C of t and then substitute 3 hours for t. We get that. And now we're using a calculator. We are substituting 3 for t, and we get that in grams per liter. Obviously, this is a negative number, and we can conclude that the concentration is decreasing.